Good afternoon, everyone. Today I will present my thesis work with the topic wood nanoengineering for multifunctionality through metallization and mineralization. I will first give a short background introduction, then the objective of my thesis, followed by results and discussion, and then the general conclusions. Hierarchical porous material is a multi-level porous system which combines the advantages of different pore sizes. Micropores and mesopores offer large specific surface area for optimal accessibility and size or shape selectivity. Macropores reduce transport limitations and facilitate mass transfer. Given the benefits of these features, hierarchical porous material have been widely used in catalyst design, adsorption and separation, energy storage, etc. However, the bottom-up engineering of hierarchical material remains a challenge due to the need to control over multiple length scales. The presence of hierarchical structure is a distinctive feature of natural system. Take hardwood as an example. Its bulk properties come from an assembly of aligned cells, mainly including vessels, fibers, and raceels. Adjacent cells are cohesively bounded by middle lamella, which is a lignin-rich area. The secondary cell wall consists of 3 layers, distinguished by their different microfibril angles. The cell wall itself can be considered as cellulose microfibril bundles embedded in the matrix of hemicellulose and lignin. Multi-scale porosity is another important feature of wood hierarchical structure. In hardwood, it spans from vessel and fiber lumen with size ranging from 20 to 300 micrometer, pits with average diameter of 6 micrometer, as well as plenty of nanopores within the cell wall. Enlightened by the naturally involved complex structure, we realize that using wood as a template is a promising strategy to fabricate functional hierarchical porous material. Using wood as a template is also economically compelling due to its renewable source, low cost, and scalable processability, which derives from the top-down fabrication. The resulting wood-based composite is also able to synergize the structural advantages of wood, such as low tortuosity and multi-scale porosity, with the functional property of guest material, leading to a hybrid system with improved properties. Among guest material, metals and minerals are of particular interest due to their potential to introduce new functionalities. The incorporation of metals and minerals into the wood scaffolds is termed wood metallization and wood mineralization, respectively. A review of relevant literature shows that the reported wood metal or wood mineral composites often either compromise the inherent pores, such as lumen space, or only depositing particles on the cell wall surface. They fail to fully utilize the hierarchical porous structure of wood, especially the nano to mesopores. This is one issue we seek to address in our work. However, the metallization or mineralization of wood, while exploiting its structural advantage, is challenging due to the limited mass transportation inherent to wood anatomy. From the flow model in hardwood, we can find that the longitudinal transport is dominated by vessels. Tangential and radial transport is enabled by pits, which created interconnected pathways between cells. However, take balsa wood as an example, which is a main wood species used in this thesis. Although vessels facilitate longitudinal transport, they have a very low fraction. The dominant cell type in balsa, which is fibers, feature a length of 0.2 to 1.2 centimeter and close ends, severely restricting longitudinal transport in thick samples. Besides, the number of pits are rather limited. Pits are also susceptible to blockage by newly formed particles, making the uniform metallization or mineralization difficult. These inherent limitations raise the demand for cell nanoengineering to introduce extra porosity and enhance the accessibility of wood. As a result, the primary objective of my thesis are to first develop methodologies for cell nanoengineering to enhance wood accessibility and incorporate functional guest material. Second, study the relationships between processing parameter, microstructure variation, and the corresponding properties. Third, explore the feasible applications enabled by the unique structure design in order to achieve the overall goal of leveraging the hierarchical structure of wood to fabricate porous functional composites. Regarding methodology development, two types of cell engineering approaches will be discussed. First, partial removal of cell components, and second, reassemble of cell components from cell to lumen to create a structure named wood aerogel. As for functional guest material, copper will act as an example for metallization due to its excellent electrical conductivity and catalytic properties. Among mineral physics, MTMS and zinc oxides are of particular interest due to their respective moisture resistance and multifunctionality. The results and discussion will be divided into 4 parts. The first is the initial demonstration to see the effect of cell component removal on preparing porous composites. A different cell engineering strategy will be used in the second part, followed by mineralization. A green and efficient approach to enhance cell accessibility will be developed in the third part. In fourth part, a one-pot approach to fabricate wood-based functional material will be discussed. Let's start from the first one, programmed removal of cell components, followed by copper plating. In this work, we used balsa wood as a starting material due to its high porosity. Chloride delignification was then performed to selectively degrade lignin. The delignified wood was then subjected to a mild alkaline treatment using sodium hydroxide at room temperature for 1 hour. From FTIR spectrum, we can see the absence of aromatic skeletal vibrations, as well as the characteristic bands of hemicellulose. Carbohydrate analysis also reveals a sharp decline in lignin content from 22 to 5%, and hemicellulose content from 22 to 8%, indicating the partial removal of lignin and hemicellulose in the engineered wood template. Using scanning electron microscope, we can observe the microstructure change on the cell wall. Delignification generates pores within the formerly lignin-rich middle-lamellar region. The subsequent sodium hydroxide treatment disrupts the intercellular connections and create extra pores. The corresponding specific surface area greatly increased from 1 square meters per gram of native wood to 70 square meters per gram, showing the efficiency of cell component removal. The engineered wood template was then used to prepare a hierarchical porous composite. Here, a low-temperature electroless copper plating was selected to decrease the rate of metal ion reduction, thereby preventing the blockage of porous structure. XRD analysis confirms the synthesis of elemental copper. The obtained composite has a reddish-brown metal-like color. In addition to the continuous coating on the surface of cell wall, a multi-layered cell wall structure embedded with copper particles was created. Besides, extensive particle fibril entanglements can be observed on the cell wall, showing the effect of deep metallization. Due to the multi-layered cell wall structure and disrupted cell wall integrity, the obtained composite demonstrates compressibility along tangential direction. The continuous coating also provides good electrical connectivity. If we combine these two features, a string-dependent electrical connectivity can be achieved. Increased strain will decrease electrical resistance due to additional connective pathways and increased material density. Different strain lead to different electrical signals, making the copper-plated wood promising as a stress sensor. Besides, the wood-based stress sensor shows quite good and stable performance over 1,000 cycles. In summary, here we demonstrate that the controlled removal of lignin and hemicellulose is an effective cell engineering strategy, which increases the specific surface area to 70 square meters per gram. With the help of cell nanoengineering and the subsequent electroless copper plating, a metallic structure that retains the multi-scale porosity can be achieved. The resulting metallic copper wood shows great potential as a stress sensor. Despite the promise, this approach has certain limitations. From material economy point of view, the significant weight loss is a drawback. Moreover, this cell engineering approach focuses on creating porosity within the cell wall. However, the lumen space, which accounts for more than 50% in most of wood species, remain underutilized. Leveraging the lumen space will further increase the structural potential of wood templates. So in the second part, we adopted a different cell wall engineering strategy to utilize the lumen space, which is achieved by extracting cell wall polymers from cell wall to lumen to create a structure named wood aerogel. MTMS mineralization strategy was then investigated to improve the properties. The wood aerogels in this part were prepared by chloride delignification, followed by cold sodium hydroxide treatment for 24 hours. The process effectively utilizes the lumen space by filling it with microfibril networks. In addition to luminar fibrils, the treatment also generates plenty of pores within the cell wall, leading to a highly porous structure with specific surface area up to 212 square meters per gram. MTMS condensation was then performed to create a hydrophobic network in order to address the inherent moisture sensitivity of cellulosic material. MTMS was selected as a sealing precursor due to the presence of methyl groups on the final silicon structure. Microscope images show that the MTMS condensation largely preserves the luminar fibrils. The newly formed spherical particles are either trapped within the porous cell wall or intertwined with luminar networks. In other words, here, in addition to cell wall, the luminar fibril networks also provide nucleation sites for particle deposition. To confirm the nature of these particles, chemical analysis was performed. From FTIR, we can see two new distinct peaks, which are associated with silicon. XPS also reveals that the binding energy of silica 2p signals is consistent with silica methyl moieties in silicon, indicating the successful coating on wood aerogel. Silicon mapping from EDX also confirms the wide presence of functional particles, both on cell wall and in the lumen, showing the effective utilization of lumen space. The resulting composite shows a combination of many interesting properties. It is highly mesoporous with specific surface area of 260 square meters per gram. MTMS condensation improves the mechanical properties of wood aerogel, evidenced by the increased yield strength and stiffness. The stiffness outperforms the reported silica cellulosic aerogel composites due to the oriented cellular structure of wood and the aligned cellulose microfibrils within the cell wall. Additionally, the contact angle on the inner part of the sample exceeds 155 degrees, while those on the surface reach up to 170, indicating the superhydrophobicity as well as the effective coating throughout the volume. MTMS functionalized aerogel also shows improved moisture resistance with moisture uptake of 26% after 4-week measurement. Moreover, MTMS functionalized aerogel demonstrates improved thermal conductivity under ambient conditions due to its highly mesoporous structure and the reduced moisture sensitivity. In summary, the cell engineering strategy used in these parts, which is extracting intrinsic biopolymers from cell wall to lumen to create wood aerogel structure, effectively utilize the lumen space and significantly increase the specific surface area, marking a great improvement over the values reported in paper 1. The obtained composite combines many interesting properties, such as high surface area, mechanical strength, moisture resistance, and good ambient thermal insulation, showing a great potential as a durable thermal insulator in energy-efficient buildings. However, the large weight loss is still a drawback. Besides, the chemical and energy consumption during chloride delignification and 24 hours cold sodium hydroxide treatment raise concerns. In paper 1 and paper 2, the cell wall nanoengineering relied on a two-step process, first delignification, followed by alkaline treatment. In part 3, we shift toward a more sustainable alternative. A one-step green and efficient approach was developed to both increase the porosity and utilize the lumen space. Copper plating was then investigated to impart new functions. Here, a one-step ambient temperature sodium hydroxide treatment was used to produce native wood aerogel. SEM images reveal that all the lumen space were occupied with microfibril networks, which can be observed from transverse and tangential planes. In addition to lumina fibril networks, the treatment generates plenty of pores within the cell wall. These two features contribute to a large specific surface area of 202 square meters per gram. To get a better understanding of this aerogel structure, we isolated lumina fibril networks from wood templates and analyzed their chemical composition. The diffusion edited NMR of lumina fibrils reveals the predominance of the acetylated xylene. From FTIR spectrum, the bands associated with acetyl groups in xylene is present in the cell wall of native wood, but absent in the cell wall of wood aerogel. This absence confirms the migration of xylene from cell wall to lumen. Meanwhile, characteristic bands of lignin and cellulose remains. In a word, the lumina fibrils of native wood aerogel primarily consist of deacetylated xylene, while the cell wall of wood aerogel is mainly composed of cellulose and lignin. The highly mesoporous structure of wood aerogel provides a great platform for subsequent functionalization. Here, electroless copper plating was applied again on the wood aerogel due to the great properties of copper. EDX mapping shows the wide presence of copper, especially in the lumen space. Zoomed-in SEM images reveal that in addition to cell wall, the lumina networks are densely coated with copper particles, also confirms the effective utilization of lumen. Hydrogen evolution reaction was then evaluated due to the electrical conductivity of copper and its catalytic performance. Here, copper-plated aerogel acts as a working electrode for water splitting. From linear sweep photometry, we can see copper-plated aerogel has better catalytic activity compared to the reference, requiring lower overpotential to reach the same current density. This favorable electrochemical performance of copper-plated aerogel is attributed to the copper-coated network and its mesoporous structure, which provides more accessible active sites and favorable mass transfer. In summary, here, a one-step sodium hydroxide treatment at ambient temperature was developed to produce highly mesoporous wood aerogel. The resulting specific surface area is comparable with the values reported in paper 2, but with a significant lower weight loss, indicating it is a green and efficient cell engineering strategy. Different with the reported wood aerogel fabrication studies, here we demonstrate that the deacetylated xylene migrate from the cell wall and reconstructed the lumina fibrils during the treatment. As the application demonstration, copper-plated wood aerogel shows favorable electrochemical performance due to the copper-coated lumina network and its mesoporous structure. From paper 1 to paper 3, the wood-based functional composite fabrication usually involves sequential steps, which are cell wall nanoengineering and functional particle deposition. In part 4, a one-pot approach was developed to combine both steps. This approach is able to simultaneously enhance the accessibility of wood and in situ synthesize the functional particles. This is achieved by the dual chemistry of zinc chloride, which serves both an agent for wood aerogel formation and a precursor for zinc oxide synthesis. The optimal condition was determined to be 78% zinc chloride at 65 degrees Celsius due to its high acidity and its wide use in vulcanized fiber production. The trapped ions here was then converted to zinc oxide by adding sodium hydroxide at room temperature. The obtained composite also shows microfibril networks within the lumen. The flower-shaped particles are distributed throughout the volume by either attaching on the cell wall or intertwined with lumina networks. XRD analysis confirms the successful synthesis of zinc oxide. Nitrogen adsorption also suggests it is a mesoporous structure with surface area of 93 square meters per gram. All of this characterization indicates that the dual function of zinc chloride is able to synthesize in zinc oxide wood aerogel composite by a one-pot approach. The obtained composite demonstrates photocatalytic degradation of methylene blue under UV irradiation. With the presence of zinc oxide wood aerogel composite, the dye degradation efficiency could reach almost 80% within first 2 hours. After 6 hours, the dye, which is outperforming the 50% of the reference. After 6 hours, the dye degradation efficiency could reach 94%, showing the photocatalytic efficacy of the composite in dye degradation. This performance can be attributed to the synergistic effect between wood aerogel and the functionality of zinc oxide. The high specific surface area of wood aerogel concentrates methylene blue molecules close to zinc oxide. The lumen, which act as aligned channels, enhances light efficiency by multiple light scattering. The flower-shaped zinc oxide was also reported to have higher catalytic activity due to its larger amount of oxygen vacancies. In summary, in this work, we developed a one-pot approach to synthesize zinc oxide wood aerogel composites, enabled by the dual function of zinc chloride. The synergistic effect between wood aerogel and zinc oxide enabled applications such as photocatalytic dye degradation. To conclude my thesis work, first we developed civil engineering approaches to enhance wood accessibility, including partial removal of lignin and hemicellulose, and creating wood aerogel structure. Using these engineered wood templates, we successfully incorporated functional guest material, such as copper and thiosinquoxin, into the wood scaffolds without compromising their multi-scale porosity. Moreover, a one-pot approach was developed to both enhance wood accessibility and incorporate functional guest material. Second, for the processing structure relationships, we especially pay attention to enhance wood accessibility by increasing its specific surface area, while for the structure property relationships, we focus on the synergistic effect between wood scaffold and the guest material. Due to the unique structure design, the obtained wood metal and wood mineral composites show great promise in a range of applications, including pressure sensor, thermal insulator, electrocatalyst, and photocatalyst. At last, I want to acknowledge the funding from Wellenberg Wood Science Center and FOMAS, as well as the support from Research. Also would like to thank all the guidance and help from my supervisors, Yuanyuan and Richard, the help from my collaborators and colleagues, as well as my family and friends. And thank you all for listening.